have like 5. Is lab going to be long?
I don't know. It shouldn't be too long.
It didn't look like it.
I don't think it'll be too long.
Okay. I don't think we have that. Did you print it? We're going to do it. It's weird.
Well, is that yeah, if you don't know what
I didn't think so. So going through my notes, I don't have chapter 5 memory. Okay, so it's, you shouldn't have to know. That's just going to be your flat right? It looks like it's the same thing as the
like different numbers and like the same thing.
we're doing like
You got like a triple.
yeah, because we should get a positive test for those things.
Well, I'm not gonna.
I could be wrong. I don't know.
Probably. So at this point, we have not gone very far on this isomer flow chart. And this is a very useful chart to determine the relationship between compounds. Normally, on this test, we actually expect you to know all of this chart. We're a little bit behind. So you will see things on this chart that are on the practice test that will not be on the test you're taking on Friday. But it is what the content of this chapter is largely about. So we ask the questions, if compounds have the same formula, we call them isomers of one kind or another. If they don't have the same formula, they're non-isomeric. We continue down, and there are 2 kinds of general classes of isomers. There are what are called constitutional isomers. And what makes a constitutional isomer? Same formula, different connectivity. And then we have what are called stereoisomers. Okay? And I kind of gave a not perfect definition of stereoisomers that if you go back in your notes and have written it down, you will find there, and we will correct that. You won't create a problem for this exam at all, but we will go back and correct that. So stereoisomers really are isomers that are spatially different. The connectivity is the same, so the atoms that are connected to atoms are exactly the same. Every atom connected to exactly the same stuff from beginning to end. But it's the orientation of those atoms in space that makes them different. And we've actually seen things like this. For example, cis and trans. Right? If we have a ring and we have 2 things that are cis, the connectivity is identical. Whether we take one of those things and put it on the opposite side of the ring, we call that trans. Those are, in fact, stereoisomers. And so what we're going to do is distinguish between those ones which are simply conformational, which rotate around sigma bonds, and those which we can classify as configurational. So a configuration is its spatial, what I will call its spatial connectivity. Rather than just saying what it's attached to, the spatial component, which direction is it pointing in? That's what I would call a spatial connectivity, not just is it attached or not. The direction that it's pointing is important. And that's where we're going to distinguish these. So conformational isomers, just rotation around sigma bonds. For example, right, if you look at equatorial and axial, how do you get between those things? Well, we say a chair flip, right? Ring flip gets between axial and equatorial. But what is really happening that's causing it to flip? It's the rotation of what? Sigma bonds. Maybe not 360 degrees, but they are definitely rotating. Same thing, conformations. Right? Just simple conformations. Gauche, anti, eclipsed, all of those are simple bond rotations. Are they different molecules? Not. They are not. They're connected identically. Spatially, you can make them equivalent by just rotating around bonds. And boat and chair fall into that. Now, things that we have already discussed, and I remember the word I used the other day, diastereotopic. Here it comes in this chapter where we talk about diastereomers. That is where that word comes from. So we will learn in detail what that is. But here you go. Cis and trans. Those things are stereoisomers because they are diastereomers, is the class of things they are. You cannot interconvert them by doing a ring flip. Remember, a ring flip is rotating sigma bonds. You cannot do it without physically breaking bonds, and that's what really distinguishes the stereoisomers. To convert between them, you'd have to break covalent bonds. Same thing here. We use E and Z. I use cis and trans. Those are more or less synonymous for this. But if I have two CH3s on the same side, these two CH3s are on opposite side, the connectivity is still the same. Right? I have this carbon of bromine, a CH3, next to another carbon with a CH3 and an H. So the connectivity is the same. But spatially, the things are pointing in a different direction. Can I interconvert these by rotating around sigma bonds? No, because a double bond doesn't allow you to rotate. And so it's stuck. And so those things are diastereomers. So the first class that we are going to go over are what are called enantiomers. That's the first thing we're going to learn about, and then we will move into the diastereomers. So here we go. We have to learn about something called chirality. Chirality. Chirality, in its simplest idea, is the concept that things have handedness, like your right hand and your left hand, right? Those have handedness. So those are actually chiral objects. Now, what distinguishes something and makes it chiral? Chiral objects, things which are chiral, lack an internal mirror plane. Things which are objects which are chiral lack an internal mirror plane. In other words, when you look at a chiral object, if you can somehow cut it in half and get it to reflect on itself, that is not chiral. Right? Because it lacks it. Right? If it reflects on itself, it is not chiral. If it does not reflect on itself, it is chiral. So let's look at some simple objects. Now, our hands, right? They are. Do they have a plane of symmetry? Do they have a? Can you put a mirror plane in your hand and get it to reflect on itself? I'm talking like your right hand or your left hand. I'm not saying between them. That's different. I'm looking at one hand and saying, is my hand chiral? The answer is yes. My hand is chiral. Because it does not have a mirror plane within it. My hand is chiral, right? It's kind of the you're looking for something that's not there to make it have a property. Okay, so let's look at these. How about this flask, this Erlenmeyer flask? Is it chiral?
No.
It is not, because if you cut it in half, it folds on itself perfectly. Now let's take, well, here's something that's not dissimilar to an Erlenmeyer flask, coffee mug, right? Is my coffee mug chiral?
Yes.
Oh, yes and no. Okay, so why do you say no? I just heard voices over here. I'm not looking at anybody in particular. Why did people say no?
It depends on your reference frame.
Friend? Okay. What? Some other ideas? Is that the only reason people said no? Everybody said no for exactly that reason. A reference frame. Go ahead.
I think it is not chiral because it does have at least one internal mirror plane.
Okay, so you think it is not chiral because it has a plane of symmetry. Okay. What? Anybody else? Take a stab at it. Nobody's even willing to take a stab at it. It's not like I'm going to come out and grab you and take away points and fail a class. Come on.
Can you say both?
Gee whiz. You guys are a tough crowd.
Can it be both?
Can it be both?
Because, like,
Interesting
if you cut
question.
it this way, it's chiral, but then if you cut it like going down where you hold it, it would be achiral.
Oh, interesting, interesting.
Is it-
Okay, that's a good point. An object will either be chiral or it won't. But it's a good point. It's a good point. So you can't have it both ways.
Is it meso?
Is it meso? No, it's not meso.
So I said that would make it chiral.
If it's meso, it's achiral, in fact. But what was your question?
So it would be chiral.
Well, I'm trying to still
Yeah. Well, could
solicit responses. So you think it's chiral?
if,
Based on what?
If chiral is like your hand, you can't. Like it's not like the flask.
Okay.
Yes. Which we said was not chiral.
That's correct.
Okay.
So you say this is chiral.
I think.
Okay, I am going to argue that it is chiral. There's no question that if I turn my coffee cup like this, I can cleave it in half. And that this side, in principle, would reflect on that side. So I'd want to say it's achiral. But what I didn't show you was the other side of my object, which has writing on it. And what happens if I take my writing from this side? Is there writing that is the mirror image on that side? There's not. It is not truly a mirror image for the whole molecule, for the whole coffee cup. So my coffee cup is chiral. It has a handedness. If it were not to have handedness, I would have to have the mirror image of this writing on the opposite side of the cup, so that when I cut it in half, this reflected onto the opposite side. Question?
So as long as you can make one cut where it mirrors, it's chiral.
It is achiral, not chiral.
It's not chiral.
Yes.
So because even if you cut it this way, it wouldn't be. That's okay because.
A mirror plane anywhere would make it not chiral. The word we use is achiral, and I have to be a little careful. So if I say achiral center, I mean not chiral, or it is chiral. So I will try and be careful. The word we usually use is achiral, and I will try and speak that properly so it doesn't sound like something in between. And if you're not sure, ask me. But this would be chiral because this does not have a reflection, a mirror on the other side. Now, if I took away the writing, I would argue that it is not chiral anymore because now I could reflect it perfectly. How about this? Chiral or achiral? Not chiral. I'll say not chiral. Chiral or not chiral? How many people not chiral? How many people chiral? I think it's chiral. Why do I think it's chiral? Because this writing on here. Now, if I took away the writing, no problem. But the minute that there's writing here, that writing would have to reflect on itself. It would have to be one of those weird things, right? Like the person is looking at. What about this? This doesn't have any writing on it other than the GIF image that I borrowed it from. So the mug itself has no writing, chiral or not chiral. Not chiral, because you can cut this in half and the two sides reflect. Spring. Chiral or not chiral? How many people say it's chiral, since I said that first? How many people said it's not chiral? It is absolutely chiral. Absolutely. Anybody heard of DNA? That's what DNA looks like. DNA has helicity, which is chiral, it turns out. So if I put a mirror plane through here, any point, you can just imagine if I put the mirror right kind of like straight through, this would not reflect onto anything. It reflect into vacant space. And so things which are helical actually have chirality. And the name that we use for that, you guys remember the quiz, right? There was D and L, E and Z. The third one was RNS. I think there's one more. It was M and P. And M and P is the distinguishers that we use for helicity. You will not have to learn those in this class, but that's how a chemist defines those. All right, stereochemistry, right? The down and dirty history. Optical activity discovered in 1891. Things that could rotate light. They were actually able to isolate in most of the natural compounds in nature. Natural, I guess that's redundant. But most of the natural compounds have a specific handedness to them, and they tend to rotate plane polarized light. So they were able to say, wow, these things have handedness at molecular level. Pasteur actually took enantiomers and separated. Quite a fascinating experiment, literally with a microscope and tweezers. He saw that these things looked like mirror images of each other. And he said, okay, I'm going to put these mirror images over here and these mirror images over there. And he found out that they rotated light differently. So quite an interesting experiment. Van Hoff, even later than that, proposed that tetrahedral carbon is what caused it. We'll take a tetrahedron apart here in a moment. And then Emil Fischer, right? Fischer, which you'll learn about, he's one of the first Nobel laureate in 1901. And then RS, Vladimir Prelog, in 1956. That's how we named them. A little bit of the guys who really were important in this. Only Fischer and Prelog have Nobel Prizes because the first Nobel Prize was in 1901. So now we have to talk about conformational isomers and configurational isomers. I already went through this, so I'm not going to go over it again. But the whole idea is, right, a conformation, right, involves rotation around sigma bonds are involved. Configurational are locked. They are fixed with respect to their orientation of groups in space. And that's what we're going to deal with here. So let's look at a tetrahedron. And this was kind of my quiz question the other day. Right? How many different groups is a tetrahedron required to have in order to be chiral? And the answer is it must have 4 different groups. Now, what is the test that we use to determine if something, or an object, in a tetrahedron is chiral? What is the test? What is the test?
Handedness.
Does it have an internal mirror?
Excellent, thank you. It doesn't have an internal mirror plane. That is the test for chirality. So what we're going to do is we're going to look at a tetrahedron and see what happens. And so I'm going to start with CH4 and ask, does this have an internal mirror plane? And I think you would agree that if I hold it like this, you can see I can divide it right down the center. Okay, what if I put one substituent and I have 3 hydrogens? What about that?
Yes.
Right? Still. What about 2 substituents?
Yes.
Right? Yeah, because I rotated this. You might see it easier that way. Doesn't matter what angle it's from, but there's a mirror plane I can put right down the middle. What if I put 3 substituents on there? There's no way. No matter how I hold it, right, I might be able to cut the middle 2 in half, but the other 2 won't reflect onto each other. So the minute that you have 4 different atoms attached to a tetrahedral carbon, you induce chirality into a molecule, or at least into the center. We would refer to a carbon that has 4 different things attached as a chiral center. It does not mean that an entire object has to be chiral, but it does say that that carbon has chiral properties. We good? So if you look at these 2 molecules, right, propionic acid and lactic acid is chiral, propionic acid is not. Because if you look at this, these 2 hydrogens, right, can be on either side of the plane, so they reflect onto each other. And these other atoms you can light up in the plane so that they can reflect. It is not a question of how the molecule is presented to you. It is a question of, can you put the molecule in a conformation, right? Can you rotate it in some manner that gives you a mirror plane? That is really the question. Just because I draw it, right? If I draw a cyclohexane as flat, right? You know, I draw the hexagon. Does that mean a cyclohexane ring is flat? No, it doesn't, right? What does a cyclohexane generally look like?
Chair.
A chair. The same thing here. You can't, just because I draw it flat, means that it has, right, it's flat. So you have to keep that in mind. So these things can have a plane of symmetry because there's a way to rotate them to get it. The easy thing to look for is, does a carbon have 4 different things attached? Does it have 4 things attached? This one has 4 things attached. It is chiral. This carbon has 3 hydrogens. It's not chiral. This one has 2 hydrogens. It's not chiral. It has to have 4 different things. This carbon, right, is double bonded to an oxygen. That's not 4 different things. This oxygen has, you know, they're not color-coded, but this oxygen has 2 lone pairs. That's not 4 different things. Has to have 4 different things to be chiral. And since carbon is bonded, it has 4 bonds, right? That's the most common. Are double bonds chiral? Are carbon-carbon double bonds chiral? That's it. It's a question. I heard 2 people respond. Are carbon-carbon double bonds chiral?
No.
So if I drew this. Is that chiral?
No.
No.
It's not. Why not?
Because it has to have 4 different.
Right? Yeah. None of the carbons have 4 different things attached. And what do we know about the shape of an sp2 carbon? It's trigonal planar. Trigonal planar. Things which are planar, right, have an internal mirror plane, don't they? They're planar. Right? The mirror plane is the plane. So things which are planar are not going to have chiral centers. That doesn't mean that chemists haven't. That's an absolute, but as a general rule, it's true. Cyclohexane. Here are a couple examples of cyclohexane. This one, it may not look chiral when it's drawn this way. Right? I should say it the other way. It may look chiral when it's drawn this way, but it is not chiral. Because if you build the model, one of those methyl groups is pointing straight up, which means the molecule can be cut perfectly in half. And so you can't, and what is the acid test? Carbon has to have what attached? 4 different things. Okay, 1, 2, those are different, but what's here? Carbon, carbon. Carbon, carbon, carbon. It's identical. Again, you can't look at that and say, well, that's what carbon looks like, right? It's not flat. You say it's a chair. What does it really look like? So this has 4 different, it does not have 4 different things attached. What about this carbon? It absolutely has 4 different things attached. It has a CH2, an H, a CH3, and a C double bond O. 4 different things. So is this chiral? Absolutely it is. So that molecule is chiral. So what are the consequences of chirality? So things which are chiral have 2 differences, and this you have to know. And next time I'm going to bring in a demonstration of this. But 2 differences when molecules are chiral. And then I'm going to define enantiomers. 1, I should say enantiomers. Anyway, first is they rotate plane polarized light. And 2, they interact differently with other chiral species. Okay, let's get down to, let's go and define a word, which is enantiomers. And we'll see how these things apply, okay, these 2 chiral molecules. And in particular, we'll talk about enantiomers with respect to that. In fact, I'm going to erase chiral molecules, and I'm going to put enantiomers. That's a better definition. Enantiomers. Enantiomers are non-superimposable mirror images. I'll say mirror image molecules. That's what enantiomers are. And so to have enantiomers, you have to be chiral. So let me do this first. Right? We said we had to have 4 different things to be chiral. And if we did not have 4 different things attached, it was not chiral. So I'm going to link that to my enantiomer quickly here. So here are, I'm going to get rid of the green one, put another one here. Now, is this chiral? No. How do I know? Okay. I'm going to see if this chiral thing is superimposable on its mirror image. And this achiral, non-chiral thing. Would everybody agree that what I have here are mirror images of each other? Right? Right? No matter, people agree those are mirror images? But are they the same molecule? And the answer is yes. They are the same molecule. Because if I take this and I simply rotate it that way, and then I've got to get it here. There we go. Rotate it that way. You can see that they are really identical. Even though I was able to make a mirror between them, they're identical. That internal mirror plane is what gives them the ability to be identical molecules. But now let's take an object which is chiral. So this is not chiral. It is going to be identical to its mirror image. Now we're going to take an object which is chiral and see what happens with its mirror image. So you take this off. And I'm going to make sure I align these correctly here. There's that. So I make the mirror images. There we go. Now, are those mirror images? So first, is this chiral?
Yes.
It is, because there's 4 different things attached. Is this chiral?
Yes.
It has 4 different things attached. Are these things mirror images of each other?
Yes.
Right? If you look, where I'm the center, right, you can see that there is a mirror plane. Are they the same molecule? And the answer is no. So when you have chiral objects, the mirror image is not the same. And the same thing is true for your hand. Is your hand chiral? It's chiral. What about your other hand? Are they mirror images? Well, pretty close, right? Within a margin of error. They're mirror images of each other. But are they the same? There is no way that you can overlap them or superimpose them such that they are the same. Right? Your thumbs don't work out. Right? You'd match your thumbs, then it's palm to palm. It's not sitting on top of each other. So they're mirror images, but they're not superimposable. Handedness, right? That makes sense. At the molecular level, the same thing is true. If you have things which are mirror images of each other and are chiral, they are not superimposable on each other. So somebody give me 2 colors.
Red and green.
Thank you. Red and green. Very Christmassy, right? So what I'm going to do is I'm going to take the red and green here, and we said these were mirror images and they were chiral. And I'm going to take the red and green here and match them up. Because if I'm going to match up all 4, I have to match up at least 2. That's the easy way to do this. So I'm going to match up red and green. Oh, that's not right. There we go. Now are my red and green matched up? They are, but what about my blue and yellow? They're not. Well, okay, give me, maybe it's a mistake. Give me 2 more colors.
Blue and yellow.
What's that?
Blue and yellow.
Blue and yellow. Okay, so let me do blue and yellow. So let me match up. Okay, there's blue and yellow. Right there matched up, but what about red and green? No, they don't match up. Okay, somebody else.
Red and blue.
Red and blue. Okay, red and blue. Red and blue. Red and butter. Okay, red and blue. I can do that. Okay. So I line up red and blue, but what happens to green and yellow? So it doesn't matter how I organize these things or how I adjust them. There is no way that I can make these the same molecule. They are different molecules. And so these chiral molecules, which are non-superimposable, right, because I can't superimpose the mirror images of each other, are what we call enantiomers. It is a result of chirality that we have this. So enantiomers are identical with these 2 exceptions. These 2 exceptions. So in other words, what if I have a boiling point? Boiling point, boiling point. Will the boiling point be different?
No.
It will be identical. What about the melting point?
Then-
What about the color?
then-
It's going to be identical. All of those physical properties will be identical. What about polarity? Identical. What about solubility? Identical. Everything will be identical except for these two things. Those things are, one, the ability to rotate plane polarized light. Chiral objects, chiral molecules, when you take plane polarized light, so anybody wear polarized, right? My Ray-Bans are polarized. Has anybody taken two polarized lenses, right, and you turn them perpendicular, it kind of blocks out the light? And the way it works is, right, the glare of the sun on the road is generally parallel, and the polarized lenses usually go this way, so it cuts out the light coming from this way, so it minimizes it to a great degree. So enantiomers have the tendency to rotate plane polarized light in opposite directions. It shouldn't be surprised, right? Because they are what? Mirror images of each other. So one rotates light to the right, the other rotates it to the left. That's it. Do you think the magnitude is different? In other words, how much? No. Equal, but opposite. The other thing that they do is they interact with other chiral objects differently. And this biochemically is huge. This is huge. And an easy example of that is, we can do a little demonstration. Right, we're all friends here. Okay? So, if you shake hands with somebody, right? Shake somebody's right hand. And I'm not kidding. Shake somebody's right hand, and then with your right hand, shake their left hand. Right? Is that the same interaction? It's totally different. Why? Because the handedness between shaking a right hand and shaking a left hand is different. That matching is different. And that has significant chemical consequences. So the interactions between these things are very different. And I'm going to bring in a demonstration. Another excellent example of that is there is odor. I have a couple of molecules in my office, like I said, I forgot to bring them today, which are enantiomers. And they smell differently. And the reason that they smell differently is because biochemically, virtually every molecule we have has a certain handedness. It is not a mixture of handedness, but it is one of the two hands that your body has. When I take these two enantiomers and interact it with the one-handedness in your nose, they interact differently, and the result is a different smell. And the only difference is the two molecules are mirror images. So the handedness of your nose is one, and you can think about the one molecule being the right hand and the other one being the left hand. And so those interactions are different, so the smells are distinctly different. They're both reasonably pleasant smells, by the way. I wouldn't do that to you. But they're distinct. You said, like, wow. And the only difference between the small molecules, the only difference is that they are enantiomers, or mirror images. And it is that handedness in your nose that makes a total difference in the way these things behave. So we'll come back to that later. Okay. And that will come back. Okay, so the next thing that we need to learn is how to assign configuration. Assign configuration. So these are what we would call configurational isomers. They cannot be interconverted by rotation around sigma bonds. Their configuration is different. So I think it would stand to reason that if I were to name, and I'm trying to get these to look like mirror images, there we go. If I were to name these molecules, and up to this point, if I had this molecule, you'd give it some name. You don't know about chirality, right? And if I gave you this molecule, you'd give it some name, not considering the fact that it's chiral. And if I gave you the mirror image, what would you name that? You'd give it the same name, right? Because you wouldn't know any better. So we need a way to distinguish them, and that's what the absolute configuration does. It distinguishes between the two enantiomers. So they have proper names. And again, it's not that they rotate. They are two different physical molecules. So let's look at a molecule. Pretty simple molecule. Could you name this? Now we're going to take the configuration out of it, but just name it not knowing anything about chirality. How would you name this?
Butane.
2-chlorobutane or 2-chlorobutane, right, if you're really cool. Right, 2-chlorobutane. However, does this molecule have a chiral center?
Yes.
It sure does. Because if you look at the second carbon, right, that carbon has 4 different things attached. And so there is this molecule, but there's also the mirror image of that molecule that we have to distinguish it from. And so this is where the configuration goes. So the way that we do this is we take the 4 groups attached to this carbon and assign priorities. Priorities are assigned using what is called the Kohn-Ingold-Prelog rules. Kohn-Ingold-Prelog, or CIP rules.
KIP?
What's that?
KIP?
Oh, yeah. It is KIP.
All right.
I don't know why I call it CIP. Thank you. Now, why did I do that? I think I've always called it CIP for some odd reason. The con is definitely with a K. Okay. Kohn-Ingold-Prelog rules. We work from the inside out. So what does that mean? It means we start at the carbon, right, or the chiral center, and work our way out. Priority is based on atomic number. So far, so good? So let's start here. Let's at least go and assign priorities. We haven't decided how we're going to really name this yet, but we have to give priorities before we can even name it. So let's assign priorities. What has the highest priority? Chlorine, right? Working inside out, chlorine. So I'm going to call chlorine priority 1. That's pretty easy. What else is that a carbon attached to? It's 2 carbons, right, and a hydrogen. Now, pretty easy to pick out the lowest priority, which is hydrogen. That's pretty easy. But now you have 2 carbons. What one does is they work inside out. That's the key. Carbon, carbon, you say they're equivalent at this point. Then you say, what is that carbon attached to? Working out. What is this carbon attached to?
3 hydrogens.
What is this carbon attached to?
2 hydrogens.
2 hydrogens and 1 carbon. When you kind of put that all together, which is going to be the higher? The one with 1 carbon or the one with the hydrogens? Carbon wins. Carbon wins. This is attached, right, to 2 hydrogens, 1 carbon. This one is attached to 3 hydrogens. The fact that you have a carbon wins. You are done. The first time you find something that wins, you are done. You do not go a single atom further. So it's not about, right, whatever else is out there. And I don't care if I have something that is, 400 times as large out here. If you find a difference on the second carbon, you are done. And that is it. And that is as far as you go. Okay, so we've assigned priorities now. We now know that this carbon is 2, and this carbon is 3, and the hydrogen's 4, right? That's how we assign our priorities. So this one is 2 because it was the carbon wins over the hydrogens. That chlorine is 1, and the hydrogen's 4. Now what one does is one rotates the lowest priority to the back. You rotate the lowest priority to the back. Models are fantastic for this. Because if this is my yellow, right, I make sure that it's in the back. Now what you're going to see, right, I've got it that way, and yellow's going to be my low priority, doesn't matter. But whatever it is, I'm going to rotate it to the back, your back, so you're looking at it. What you see are 3 other atoms in the front and 1 in the back. Right? 3 in the front, 1 pointing away from you. It is the orientation or the organization of these 3 which determines the configuration. So I'm going to redraw this a little bit. It is not necessary to redraw it, but if I do it, I'm going to say chlorine is up, my CH3 is here, my CH2, CH3, and my H is back. So from that point of view, right, if my H was, this is kind of what I had, I'm going to, kind of like this, people, right, that's these are in the plane. Right, these 2, the green and the red are in the plane. The hydrogen is in the back. My chlorine is blue pointing out at you. That's what that is. Now what I'm going to do is I'm going to rotate this hydrogen into the back. So that chlorine is now pointing pretty much straight up. Right, this one is kind of like a Newman projection, right, with the hydrogen in the back. And then that's what I would see. Hydrogen's in the back, the chlorine's in the front. I should probably draw that as a wedge. And my priority is chlorine 1, this 2, that 3. If the priority 1, 2, 3 is clockwise, it is called R, the R configuration. If it is counterclockwise, right, going from 1 to 3 again, from highest to lowest priority, then it is S configuration. Right, that's the mirror image. That will be the mirror image. So for this molecule, the configuration is R, because we've assigned it. And so the name, the proper name is R, you put it in parentheses, 2-chlorobutane. And what would the enantiomer be called? S2-chlorobutane. Question?
Is the chlorine, like, would that still be coming forward, like it still would be a wedge?
Technically, yes, but it's kind of like, I'm trying to draw this more from the point of view of a Newman projection. Right? The Newman projection, even when we look down a Newman projection, all 3 are actually pointing at you. But we draw it flat. So I'm only trying to show the priority. I'm not trying to, I've got the original structure. I understand what you're saying. It doesn't look much different than that if I do it this way. So I'm just trying to say, those are the 3 I'm focusing on, the hydrogen in the back.
Okay.
Yes?
If it was 3-chloropentane, would that still be chiral?
It would not.
Okay.
Excellent question.
Just want to be on track.
Yeah, you're right on track. Right? Is that chiral? It is not. It is not chiral, because this carbon is attached to 2 identical things, CH2, CH3, CH2, CH3. Is this chiral? Or does it have a chiral center? Right, that's where we're kind of starting. It does. It does. Because even though it's super far removed, there is a difference. Right, this has 4 things attached. 4 different things. This has CH2, a CH3, an H, a Br, and then a bunch of carbons in a Br. In order for it to be achiral or not chiral, right? 2 of those things would have, at a minimum, would have to be identical. and it has to be completely identical. So don't get your question. Don't stop looking just because you get to the first carbon and say they look the same. You have to make sure that it is different somewhere. And if you have to go to the end of the molecule to prove that, that's what you have to do. Yes?
So is the one that we've been working on, is it chiral because they both, it has 2 carbons attached to it. Is it because one of the carbons has another carbon attached to it?
Yeah, absolutely. So they're not identical, right? One's a CH3, one's a CH2CH3.
So even if that was on this one, if it was CH2CH3, it would still be chiral.
Yeah.
Because it's different.
If I put the same number of carbons out here that are over here, and this one had a bromine and that one did not, it would still be chiral. Because one would be a chain with no bromines, one would be a chain with a bromine, and that makes them different. Now, is this one chiral, this center? Right, a molecule, does that seem reasonable, can have many chiral centers, right, and not just one. Is this center chiral? We said this one was. How about this one on the end?
No.
No, why not?
There's 2 hydrogens.
It's got 2 H's.
So in the owl, there was one that had like 10 chiral centers.
Yeah.
Does the presence of more or less chiral centers contribute to stability at all?
No,
No.
has nothing to do with stability whatsoever. Totally unrelated. Now, the number of stereocenters can be unrelated, but the configuration could be related. And it's not an obvious or intuitive because it represents a 3-dimensional structure, right, when you have R and S. And you can imagine if I've got 2 chiral centers that point 2 large groups towards each other, that's going to increase a lot of steric strain, and so that would destabilize it. But you can't tell whether it's going to be an R or an S that's going to do that. So configuration can have an impact of stability, but there's no general guideline you can say, well, I know this many chiral centers makes it more or less stable. There's no correlation whatsoever. But great question. Okay, so let's look real quickly at another example. I have no idea what the answer is. Is this molecule chiral, or does it have a chiral center?
Yes.
Yeah.
Yeah. How many?
3.
It actually has 2. I didn't define that, but it would be chiral center because it had 4 things attached. Now I've defined it. Before, it could have been either one, but it definitely was chiral, 4 things. Okay, let's assign configuration. Now I want to assign the configuration for this one because it'll be more, brings up more stuff. So what do? We go out from the carbon, right, and start counting. So carbon, carbon, carbon. So we still don't know what number 1 is. What is this carbon attached to? An oxygen. What is this carbon attached to? An oxygen. What is this carbon? Hydrogen. So that one's going to be lower, right, because just hydrogens. The question is what to do with this. So what happens is when you have a multiple bond, they're counted multiple times. So when I ask, what is this carbon attached to, what should the answer be?
2 oxygens.
2 oxygens, and depending on whether you're counting forwards and backwards, right? A lot of people like to count forwards and backwards. 2 carbons. Right there. Carbon from which it came and the carbons to where it's going. What about this carbon? An oxygen, a hydrogen, and 2 carbons. Which wins? The double bond O. Why? Because it's bonded to 2 oxygens rather than 1. So it wins. Do I need to go any further? I do not. I stop. So this one, right, is 1. You know, I'm going to make my life interesting here. It won't change the 1, right? Number 2 would be this OH. Everybody okay with that? Would be the carbon where the OH is, would be number 2. Everybody okay with CH3 being 3, hydrogen obviously 4? Let's try that again. Now, what is the configuration?
That's
Yeah. Because 1, 2, 3 is counterclockwise after putting 4.
Okay, the configurations are. Because what rule did you forget? You forgot, or individuals forgot. You always put the lowest priority where?
the back.
In the back. And in this,
Oh,
it's
that would've-
pointing to the front.
That would have flipped the others.
And when you do that, right, if you look at the back, the red and the blue are here, so it's red, blue, green that way. But if I rotate it so that's in the back, then it's red, blue, green, the opposite direction. So you have to make sure that you get that hydrogen or that lowest priority group in the back in order to assign configuration. If you don't, you can mess up. Good?
If we kept it the way you had it before, would it be an S then?
If, yes, if it was the original structure, such that the H was in the back, it would be an S. This is the mirror image. Actually, we'll talk about that. If you take 2 groups on a chiral center and swap it, you make the mirror image. We'll do that experiment next time. Bring models, very useful. In order to assign configuration, you can kind of go and listen to this. I'll mention it again. In order to assign configuration for anything, you need nothing more than a tetrahedron. I don't care how big the molecule is. You can solve it with a tetrahedron. So you don't need to build an entire molecule to figure that stuff out. So I'd encourage you to bring a tetrahedron to class next time. At least 2 of them, because we're going to talk about isostereomers. And that will be helpful.
Are the practice exams for STEM and SIM different?
They are the same.
They're the same?
They are the same.
Okay, so the one tomorrow is the same as one tonight?
That is correct.
Are you going to Yes.
You may.
Can I be a little bit late?
You're welcome.
Well, it depends. I'm all allowed to. I got a lot of Where's the NMR lab?
Which section are you in? Today? 5 o'clock? You need till tomorrow? I can do till tomorrow.
I wrote down about
Right.
yeah, that's fine. That it was Monday.
Tomorrow. Bring it tomorrow.
Okay.
And you'll be fine. You're welcome.
The exam doesn't cover 5, right? Just 11.
Exam will not cover 5.
I mean, don't but we stuff more to do.
I can't, well, okay, here's what I will tell you. It can't cover 5, but you need to know what stereoisomers are because we talked about system trains and chairs.
Yeah.
So I don't want you to think, well, because that's in chapter, but we did cover that material, so that stuff is a little overlap, but nothing more than that.
Okay.
I wanted to see if this was right from the review session this morning.
Okay,
From
give me
the
just a moment to
That's fine.
stop this.